This video is about chemical reactions and their reaction rates. So this is how fast it takes for that reaction to actually occur. Now, some reactions, which are most of probably what you've seen, react fairly quickly, but some take extremely long time to actually occur that you may think it might not happen. There's several reasons behind this. There are several ways to speed up reactions and so forth, so that's what this video is on. So before you can actually have a chemical react, you have what's called the collision theory. And I like to compare this to meeting people. Now this is a little bit different now with the internet, but if we were to get rid of the internet, so go back however many years, the only way for two people to actually meet is if they come in contact. So chemicals are the same way. The only way two chemicals can actually meet and react is if they actually collide and come together. Okay? So the collision theory states that reaction rates depends on the collisions between reacting particles. Just like a relationship, it depends on how you came together and the circumstances and the environment and so forth. Okay? So a successful collision, first they must collide with each other. If there is no collision, there is no reaction. Then they have to have the correct orientation, meaning they have to have the correct position. So certain atoms have to face certain atoms and so forth. And then lastly, you have to have enough energy. If there's not enough energy there, if it's boring or whatever else, there's not going to be any sort of reaction going on. Okay? Now, a key thing is that energy piece, aka activation energy. Activation energy is the minimum energy required for a reaction to occur. If that activation energy does not reach, the reaction will not happen. So activation energy, if you see this graph, which another graph for this unit, is always from this line to the top of the hill. Okay? It's always from this first plateau of the graph to the top of the hill is the activation energy. Over here, if you can tell, you start off with chemicals. These are your reactants. The first plateau are your reactants, and then energy increases fairly quickly and gets to the top of this hill. Again, activation energy is always from the reactants to the top of the hill and then decreases. This plateau are your products. So what this is telling you is wherever this plateau is, that's the energy of the reactants. This plateau tells you the energy of your products. So if in this example, your reactants are sitting at 0, here your products are sitting at 60. So there's a difference there. And then activation energy from the bottom to the top of the hill. Now, the activation energy depends on the reactants. The lower the activation energy, the faster the reaction rate. Okay, so compare this hill to, let's say, we draw a little tiny little speed bump type thing. Okay, which one would be faster to go over? The small tiny speed bump, right? Because it doesn't take much to get over it. So the smaller the activation energy, the faster the reaction rate. Another thing that changes reaction rate is surface area. The higher the surface area, the faster the reaction rate. Because, and I've seen this on the end of exam, the final exam several times, on the practice exam, on the release questions and so forth, they always have questions about what I'm going over right now. So you have to know not just that they do this, but why. So surface area increases because more opportunities for collisions. You're breaking it up. So for example, sugar cube versus tiny little particles. Okay, if you were to break this up, you still have the same amount. Okay, same amount of sugar is in there, but if you break it up, you're causing more surface area to be there, so there's more opportunities for collisions. And we talked about this before. The way to increase surface area is either using smaller particles or dissolve in the water. Okay, next, another way to increase is concentration. Now remember, concentration is about the amount of stuff. So the higher the concentration, the faster the reaction rate. Higher concentration, faster reaction rate. I like to compare this to the hallway. If you go walk in the hallway to go to the bathroom during class, there's hardly anybody out there, you're not going to run into anybody. But if you go walking in the hallway when the bell rings, you're more likely to collide with somebody because there's tons of people out there. Okay? So the more concentration, the faster reaction rate. And that's what this picture is showing. Okay, here it's hardly bumping into anything because there's hardly anything there. And then here, there's everything. It's like traffic on a holiday weekend. You always get backed up and there's accidents and so forth because of that concentration piece. Then temperature. The higher the temperature, the faster the reaction rate. Because remember that higher the temperature means your particles are moving faster. And if they're moving faster, they're going to hit each other more likely, and they're going to reach that activation energy a lot quicker. Okay? And then last, you've been doing these catalysts all semester long. And why are they called catalysts? Why do I call my warm-ups catalysts? It's because it's supposed to, now the key word is supposed to, get you started, get you moving, and get you into the class already. So it's supposed to speed you up. Now, the real catalyst in chemistry is a substance that increases the reaction rate without being consumed. This is the key thing there. It's not actually about the chemical reaction. It's not in the chemical reaction. It's simply being used to increase the reaction by lowering the activation energy. This is another thing. They always ask about what a catalyst is. Now, another key word, I think I spelled that wrong. Sorry. I'm not sure on my spelling here. Sorry. Enzyme, which is what you learned in biology. That's just another word that they use for it. In the curriculum, they say catalyst, but in the practice exams, I've seen them use the word enzyme. So you got to make sure that you know both those words. Okay? All right. So we need to talk a little bit more about these graphs. And these graphs are called reaction pathways. And so like I've said, it shows the change of energy during a chemical reaction. Over here you have your reactants. Over here you have your products. And then this energy here, this hill, is talking about your activation energy. Now, I'm going to give you a graph, and you've got to be able to tell me whether it's exothermic or endothermic. And we've talked about these words before at the beginning of the unit. Remember, exothermic means releases energy. This means energy decreases in the actual system. It goes down. So if I give you a graph, and I'm going to make this a little bit darker so you can see it on the video here. If I give you a graph, and it looks like this, where your reactants are higher than your products, that means your energy decreased. Your energy, your overall energy of the reaction went down. It lost energy. This means it was released. So if I give you a graph that looks like this, so if I were to redraw it just simple, like that, energy goes down, that is exothermic. Means energy has been lost. Okay? Now, another way that you should be able to tell me if something's endothermic or exothermic is by looking at the chemical reaction. So this is a chemical reaction that we've been doing, but it has something extra in there. This word energy. If this word energy is a product, meaning energy is on the right side of the arrow, this means it's being produced, it's being released. So if energy is a product, that means it's exothermic. Energy is product, exothermic. And then if you can remember one, you should be able to remember the other one. Okay, so let me redraw this a little bit darker. So this time your reactants are starting here, products are there. So energy has gone up. It has increased because it's gone into the system. It's endothermic. Energy has been absorbed. Okay, so if energy goes up, so if you were to redraw this, it looks like that. It goes upward. It's endothermic. Okay, then also looking at a chemical reaction, if energy is a reactant, meaning it's being taken into the system, then it's endothermic. Now, I also want to emphasize this because it's a little bit easier to see here. This line here, this arrow, is your activation energy. Remember, it's always from the reactants to the top of the hill. Just this part right here. This doesn't mean anything for the activation energy. Okay?